wrong button. Here we go. So let's say we have Denver. That is an ugly N, V-E-R. All right. Denver, they used 7,000 megawatts of electricity per year. A megawatt is, of course, 1 times 10 to the 6 watts. That's a lot of watts. Okay, and let's write a power function for any time t after 2010, let's say. Okay? And so we will say the power function p of t will equal p of 0 times what? E to the kt. You've heard of HERT. Oftentimes in books they'll use k for constants. So this is very similar. The amount equals p times e to the rt is maybe what you're more used to. Is that okay, Abby? You've seen that? No crisis? Okay. So Denver expects 2% growth in consumption. You know, and again, we try, it's very interesting. They try to have all these energy saving appliances and things, Energy Star stickers. You've seen those, Kyle. But people still keep buying more and more crap, and their cars use more and more electricity because now not only do you have the heated seats, you have the cool seats. Everything uses more. You got to have the big loud speakers, and jeepers, keeps going and going. Yeah, it seems like. Okay, so we know if a 2% growth rate, we can then figure out what k equals. Because we can say p of 1 equals 7,000 times 0.02 equals what about? Somebody help me out with that. What do you got? Okay, grab that for me. Or, yeah, 1.02 is easy. I was going to add it, but that's easier. So, how much? Did you do the 1? Yeah, no, it's 7140. Should be 7140. Yeah, that's right. And you could have taken 0.02 and you would have gotten 140 and then added it to 7,000. That's fine too. Same difference. Okay, so we can say then that, or if you're going 7140 over 7,000, you'll get 1.02. Same difference, okay? So then you can say, oh, okay, that's cool. So then what does k equal? How can we figure out k? We can say 7140 is the amount we have after 1 year equals 7,000 times e to the k times 1, because we knew that was 1 year. And we can figure out that k rate. Boy, this is going slower than I had hoped. So everybody figure out k. Don't be packing up. K, Lee. Figure out k. Okay? So what does k equal? So 7140 over 7,000 equals e to the k times 1. So let's find k. What do we get? You can. 1.02 equals e to the k. Then what? Natural log 1.02 equals natural log of e to the k. equals K, exactly right. So K is approximately, ah, we'll continue. We'll continue. K is approximately 0.0198. Hey everybody, we ran out of time, so I'll put tonight's homework assignment on the line. How about I'll just add it to this video? Yeah, I'm gonna pause this. Okay, so we ran out of time, but I'm going to continue on with this video. So we have K is approximately equal to 0.0198. And then, now that we have that function, we can do all kinds of tricks with it. So then we would have P of T, the amount of power consumed in Denver with respect to time, equals the amount they consumed in 2010 times E to the KT, and our rate is 0.0198 T. So this will give us the amount of power consumed by Denver residents anytime after 2010. We're saying time T greater than or equal to 0 years. Okay. So this is nice. So 2010 would be year 1. 2011 would be year 2. 2012 would be year 3, etc. There's where our T is. So a nice use for this would be to find out the total amount of energy used in any one year. And for that, it's a sum, obviously. And if we were talking about 2014, that would be years, or year 4 to 5, really, if you're talking about an integral, 4 to 5. So we could say year 4 to 5, the amount of power consumed, the sum of that, the integral, the definite integral, tt. So we can get more specific than that. We can say the definite integral from year 4 to year 5, which is 2014, of 7,000 times e to the 0.0198. That's our k, or our rate, constant rate, times the number of years t, dt. And I like this one because we were a little shaky last week on e to some more complex power, not just e to the x. So we have the coefficient in front of that t to deal with. So let's see what this looks like. Well, to begin with, I would probably, you don't have to, but I would probably move the 7,000 outside. And then we have e to the 0.0198 t dt. So whenever it's complicated like this, I like to do a substitution. So I can say let e to the u, or more properly, let u, I wanted green, man, I'm having problems. Let u equal 0.0198 t. Then du dt equals 0.0198, and du equals 0.0198 dt. Okay, this isn't too bad. I mean, it's going to need a little bit of work, but nothing serious. So now we have 7,000 times, and I'm going to put A to B here because my limits of integration would change. E to the U, that's good. But then notice, in order to have du, I would need 0.0198 dt, and right now I just have dt. So let's force this to be correct by putting in, multiplying dt times 0.0198, and then compensating for that by multiplying by its reciprocal out here, 1 over 0.0198. And now I have, and I have to do the same thing, I have to carry that down, carry its reciprocal down. And now I have e to the u du. E to the u du, that's nice. This can remain out there for the time being. That'll be all right. So life's good. So now I can say this is 7,000 over 0.0198. I don't even care what that is. Times, I'm ready to go, I guess. I was going to rewrite the integral, but I don't have to. Times e to the u, evaluated from A to B. And since that's done, then I can say 7,000 over 0.0198 times e to the 0.0198 evaluated from 4 to 5. So that just gives me 7,000, looks like 7,600, 0.0198 times e. Oh wait, I think I made a mistake. I think I left off a t. Man, I started thinking, where's my t? So yeah, u was 0.0198 t. So that way I can substitute in 5 and 4. But, that was not crucial. Here we go. Got to have it. 0.0198 times 5 minus e to the 0.0198 times 4. And when you crunch those numbers, you'll get 7,000 over 0.0198 times approximately 0.0216. And then that is 7,652 megawatts of energy consumed during the year 2014. Pretty cool and pretty useful. Anytime you're trying to sum up anything, integration is wonderful. So that's it for now, but I did promise you that I would come up with the new assignment. So Mr. Hartman, would you hand me that calculus book there, please? And I'll just take one more minute and I'll be done. And y'all can have a new assignment. You tennis people, hope you did well in Woodburn. But when you're sitting around bored waiting for the bus, you can start in on your assignment. 6.2 homework, which is, oh, we're getting to the good stuff pretty soon. Let's do, that's an interesting comparison. Yeah, let's do 1, 3, 11, 13, Well, we got to keep doing some slope fields. Definitely. 15. Yeah, that one's pretty fast. 19. 21, 23, 20. Whoa, that went away. 27. Oh, I think I'll skip that. 41. I think I'll skip that. 49. And, ooh, population, I like that. And 57 through 61 and 63. Okay, that'll be good. Cool. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's not bad. 17 problems. Some of them take a little bit, but that's not bad. Easier than last time. Okay, so that is all we have for today. Please work on that 6-2 homework tonight and enjoy. Thank you. Where is my smart recorder? There it is. 17 minutes, not bad.